3.2. Okay, 3.2, we are now looking at polynomials. Again, quadratics are technically polynomials, linear equations are technically polynomials. We are just, we're calling polynomials anything that's not a higher degree than, that is a higher degree than quadratics or linears, third degree, fourth degree. Anything higher than that, we just kind of lump all together into polynomials. So just like we did in 3.1, we were graphing quadratics. Now we want to look at little higher degree functions and be able to graph those. It's the same idea as 3.1, except different kinds of functions. So the things we're interested in now is what was listed there: end behavior, zeros, multiplicities, intermediate value theorem. So let's look at what's going on there. So first of all, what is a polynomial? A polynomial function, this is 3.2. We call polynomial functions anything that has something like this. So if we say f of x, like in the book, you're going to see this long definition of what a polynomial function is. And it looks something like this, where we have a coefficient in front of a variable raised to an exponent. And then we keep going down by 1. So let's say this, this is n, and this one's going to be n minus 1 times x to the n minus 1. And then we keep going until we get down to a to the first, a sub 1 to the x, and then a constant term. And x to the 0, remember, is just 1, so really it's just a constant term here at the end. But what all this really means is something like this. So for example, this is a polynomial. If we have, say, 7x to the 6th plus 4x to the 5th, and we don't have to have every exponent term, let's say 2x squared plus 3x plus 7. Okay, that's all this expression in your book on page 348 is saying. I mean, you look at this and a lot of people get intimidated by this because of all the letters and numbers and everything else, but all it's doing is expressing something like this. Here we call this the lead coefficient. Lead coefficient. So it's the number in front of the variable with the highest exponent. We call this the degree of the polynomial. The highest exponent on the variable is called the degree of the polynomial. So here the 7 is the lead coefficient. The degree of this example is 6. Each one of these is a term, just to get our notation straight. This is one term, this is another term, and so on. This is a coefficient, this is a variable, that's an exponent, right? Just to get our nomenclature right. So this is what we're interested in trying to graph now. I just made this one up, we're not going to do this one. But what we want to identify here, basically, when we're trying to graph polynomials, is first we're going to look at what does it look like at the extremes. When we go out towards x equals infinity or x equals negative infinity. What does it do? Because polynomials are always going to, the domain of any polynomial is always all real numbers. So domain of any polynomial is all real numbers. Everything from negative infinity to infinity. So it's either going to go up toward positive infinity as it goes out, or down. And that's the first thing we're going to look at. And the same thing over here. Is it going up or is it going down? And then we're going to find the x-intercepts, the y-intercepts, and kind of connect the two ends together. Now, examples of functions that are not polynomials is anything that doesn't have a whole number exponent, like any fractional exponents. They're not going to be polynomials. Those are radical equations. Anything with variables in denominators, rational stuff, that's not a polynomial. So examples of functions that are not polynomials. Polynomials is something like anything that has fractional exponents. Right? This is not a polynomial. because of the fractional exponent. Okay, anything with fractions. Okay, this is not a polynomial, right? Not a polynomial. So we've got some other good examples in here. Yeah, it basically covers it, right? Anything that has variables in a denominator, these are rationals, these are not polynomials. Rationals, these are radicals, these are not polynomials. So we're just looking at polynomials in this section. Okay, so let's look at a couple problems. All right, so first we're going to start with the extremes, like we said. So we call this end behavior. What does the polynomial look like at the ends? And there's a very nice table that explains this fully on page 350. So what did I say? Number 20 deals with this. So we're given, this is number 20, on page 360, we're given this function, 11x cubed minus 6x squared plus x plus 3. All right, so that is a polynomial function, right? There's no denominators involving variables, there's no fractional exponents, this is a polynomial function. So our task is just in this question, just to find out what does it look like on the end. So there are 4 possibilities. And again, this is nicely illustrated on page 350. So we're going to look at the lead coefficient, which we just determined, and the degree. Right? Those are the things that we need to look at. Right? So lead coefficient and the degree. All right, so we'll look at each of the 4 cases. So we're going to let's call the degree n, and we'll call the lead coefficient, let's see, we'll use certain letters in here, just try to be consistent with the book, a sub n. We'll call this, remember that was the lead term in the generic form of the polynomial. Okay, so first case, if the lead coefficient is positive and n is even, we'll list the possibilities first and then we'll show which is which. Here, lead coefficient positive and odd. Third case, lead coefficient negative and even. And fourth case, lead coefficient negative and odd. So those are the 4 cases. And again, there's better pictures of exactly this on that page. Okay, so basically we're just saying, what does it do as we go out to negative infinity and go out to positive infinity? And what happens with the polynomial is when we have it in what we call descending order, okay, highest term, the term with the highest exponent first. That's called descending order. It's important to put your polynomial in descending order of exponents, 3, 2, 1, constant. If it's not in that form, you want to do that first. At least the lead term is the most important. So lead term has this lead coefficient and the degree. And the lead term is going to dominate any polynomial because as we go out to positive infinity or negative infinity, the numbers, the magnitude of the numbers are so large that if we take, say 10 million and raise it to the third, that's going to dominate the rest of the polynomial. The rest of the polynomial isn't going to matter at that point when we go out to the really large values to the right or the really large negative values to the left. So all we're looking at is saying, what does this lead term do as I go out toward positive infinity? Okay, so positive number, so here we got positive lead coefficient, even exponent. So if we go out and say, put 1,000,000, and x equals 1,000,000 into a polynomial that has a lead coefficient that's positive and an exponent that's even. So 1,000,000 raised to an even exponent is still going to be a very large positive number, times a positive number. So it's going to go up in that direction. For the n being even, this case and this case, in this case, they're both going to rise to the right and to the left. And here, because the lead coefficient is negative, and we're putting a large x value in raised to an even power, it's going to go down in both directions. Okay, so when n is even, they're either both rising or both falling. When n is odd is when you're going to get one rising and one falling, depending on what the lead coefficient is. So here, we have a lead coefficient that's positive and a degree that's odd, which is the case we have here. So if we put a very large x value in, we get a very large x value, positive, raised to an odd degree, so still positive, times a positive. So it goes up, and then the other direction it goes down. Because if we take a negative value and raise it to an odd exponent, we get a negative value times a positive, which tells us it goes down in that direction. And the opposite over here, going up in this direction and down in this direction. So that's what we're talking about with n behavior. And again, there's a very nice table set up explaining exactly this on page 350. So that's where we start. We want to graph a polynomial equation. So we're going to first determine which one of these four cases we're dealing with. Then we're going to find the x-intercepts and the y-intercept and kind of connect the two ends. Now another thing about polynomials is polynomials are always what we call smooth curves. Right? A polynomial will never have any breaks in it, like a rational equation. For instance, polynomial, again, you can draw a polynomial if it's rising, going down and then going up over here. We know that from here to that end, you're never going to have to lift your pen off the paper. Right? It's going to do something like this. Right? We don't know exactly what, but there's no breaks. Right? This is a polynomial. We call it a smooth curve, as opposed to a rational, which might look something like this, right? Where there's a break in it. This is a rational function, not a polynomial. So we use this fact that it's a smooth curve to know that from here to here, we're never going to have any breaks. From here to here, there's not going to be any breaks. So I know if there's an x-intercept here and an x-intercept here, there's not going to be any positive values between here and here, because it's a smooth curve. So we use that fact. Okay, so that's n behavior. We find the n behavior, then we have to use our knowledge of factoring to get the zeros, which give us our x-intercepts. Y-intercept is generally pretty easy to find. We just set x equal to 0, and then we connect everything and get a sketch of the graph. So let's look at how to do that. First, we have to practice finding zeros. So let's do that first. So finding zeros was for quadratics, right? It wasn't that hard because we could generally use the zero factor property or the quadratic formula to find those values which gave us outputs of 0, which give us the x-intercepts. But now we're talking about higher degree polynomials, so we have to remember our factoring a little bit more. So let's look at number 26 on page 361. Okay, 26. So we're given this function x plus 5, x plus 2 squared. Okay, so the question here is to find the zeros. And zeros are the x values that give f of x equaling 0. So we want to find the x's that when we put it into the function, we get f of x equaling 0. Now this one's nicely factored, right? The first thing we want to do is factor. This one's already factored, right? So we got no problem here, right? This one's already factored. So we know immediately, this using the zero factor property, this factor equals 0 when x is negative 5. Right? This factor equals 0 when x is negative 2. We're done. Right? So zeros are at x equals negative 5 and x equals negative 2. Now we're also interested in something called multiplicities of the zeros. So multiplicities we're going to use when we graph the function. The multiplicity of the zero is going to tell us whether when the graph hits that x-intercept, does it cross the x-axis or does it hit it and turn around? That's what the multiplicities will tell us. So here, notice the x plus 2 factor appears twice. Right? It appears twice. So we say the 0 of minus 2 has a multiplicity of 2. The negative 5 factor, the x plus 5 factor only appears once. So we say that has a multiplicity of 1. So notice something here, the multiplicities are always going to add up to the degree of the original polynomial. Notice here we have an x to the first and an x squared. If we were to multiply all that out, our lead term would be an x cubed, right? X to the third. So our degree here is 3. The multiplicities will always add up to the degree. That's always going to happen. Okay? So the zeros, so these are the factors. So the linear factors, I want you to keep these three things distinct. So linear factors are the 3, we don't really care about that because there's no x involved. There's an x plus 5, and there's 2 x plus 2's. Right? Those are the linear factors. So if you're asked for the factors, you don't have to list these twice, but you want to notice that it has a multiplicity of 2. You can write it like this, but you want to remember that the multiplicities are important. You can write it like this if it helps. So these are the factors. Okay, the factors lead to the zeros. Okay, once you know the factors, you set each factor equal to 0 to get the zeros. Okay? The zeros lead to the x-intercepts. All you do is put a y equals 0 in for each x. So x-intercepts are at negative 5, 0, and negative 2, 0. All right, so 3 different things. I want you to keep those things separate. If you're asked for the factors of a polynomial, this is what you're being asked for. If you're asked for the zeros of the function, you're being asked for the x values that make the factors equal to 0. And if you're asked for the x-intercepts, be sure that you give ordered pairs as the x-intercepts. All right, so we determined that this function has zeros at negative 5 and negative 2, which tell us the x-intercepts are here, and we know the multiplicities. So now, if we were to try to, so that was all that was asked in this question, but let's take it the extra step and practice our graphing of this type of equation. So if we were to graph this, then first we want to look at the end behavior. So we're going to say this is the f of x function here. Now, when it's factored like this, it's not as easy to see the lead term, right? But the lead coefficient is still here, right? The lead coefficient is 3, so our lead coefficient is positive, and our degree, a lot of people will look and say, oh, it's degree 2 because that's the highest number that I see. But you got to be careful. When you multiply this by this, you're going to get an x squared and then another x, so your degree here is 3, right? So here our lead coefficient is 3, which is positive, and our degree is also 3. So looking at the end behavior model, if we go out to large x values, we're going to get a positive value times a positive value raised to an odd exponent. So it's going to rise to the right. And since the degree is odd, it's going to fall to the left. Again, look at that table of end behavior if you still don't see that. We've already found our x-intercepts at -5 and at -2. So we got an x-intercept here at -5 and an x-intercept at negative. We'll label everything at the end so we don't get in the way of trying to graph it. And the y-intercept is generally pretty easy to find. Again, we set x equal to 0. So here we're going to get f of 0 is going to be 3 times 5 times 2 squared. So that's going to be 15 times 4, or 60. So our y-intercept is at 0, 60. Okay, so somewhere way up here. Put this a little higher to account for that. So now, like we said, the multiplicities, since we know it's a smooth curve from here to here, we're never going to have to lift the pencil off the paper. So we know from here to here, and it's not going to be exact, right? We're only getting an approximation of what it looks like. But we want to get the intercepts and everything correct. So over here at -5, 0, it had a multiplicity of 1. So it crosses the x-axis. So multiplicity odd means it crosses the x-axis. Odd. Even means it turns around if m is even. All right, so at -5, it crosses the x-axis. Now, we don't know exactly what it does between here and here, but we know it's all positive, right? So we don't know how high it goes, but we know it's all positive until it comes back there to -2. But at -2, it has an even multiplicity, so it doesn't cross, it turns around. Right? So it hits and turns around because of the multiplicity being even, which luckily fits with our y-intercept. It's always going to cross the y-intercept. It's never going to turn around. And then it meets up over here. And again, if you put that in your calculator, you might see something a little different, but you're going to see the x-intercept at -5, another x-intercept at -2, a y-intercept at 60. And it's going to cross the x-axis here, and it's not going to cross the x-axis here because of the multiplicities. Now another test to see if you're right, and this is probably a little bit more like this. Another test is the number of turns in the graph. Like this is a turn. It's going from rising to falling and from falling to rising, so it's got 2 turns. And again, this isn't really a turn, it's just more of a straight up like that. But it's going to have at most 1 less turn than the degree. That's just another way to check to see if it's within the bounds of correctness. 1 turn, 2 turns, 1 less than 3. At most, it's going to have 2 turns. That's just another way to check. All right, let's do one more of these to practice. Let's look at number 42. Okay, that's a good one. Number 42. So we're going to do the same thing. We're going to graph this as best we can. Page 361. And now this one is not already factored for us. So we got a little bit of extra work to do to get the factors. All right, so same idea. First we want to, well now the lead coefficient and the degree are more visible, right? So immediately we can look at the lead term here and say our lead coefficient is 1, which is greater than 0, and our degree is 3. So those are kind of the first things you want to notice, especially when it's in this form. Descending order again, remember, descending order, 3, 2, 1, 0, in terms of exponents. All right, so our end behavior here, we have a lead coefficient that's positive and an odd degree. So our end behavior is going to be, looks like rising to the right, right? If we put a million in here, a million cubed is a million cubed times 1. So that's a large positive number. If we put a negative 1 million in, negative value raised to an odd exponent is negative times that 1, shows us it's going down to the left. Okay, so to find the zeros and the multiplicities, we need to factor. All right, so once again, factoring, prerequisite from chapter P. Got to remember how to factor. I keep saying it comes up again and again. Once again, here we got 4 terms. So your clue to factoring that generally is grouping. Now again, it's not always just the first 2 terms and the second 2 terms, but that is looking pretty good in this case. If we group the first 2 terms together and then add the second 2 terms together, we can use grouping to factor that. So we can say greatest common factor of those first 2 terms is x squared. And we get x plus 1. And then if we, now remember the clue, the goal is to get this same binomial over here. So if we take out a negative 4, that will work best. We'll be left with the x plus 1. Right? Negative 4x minus 4. Negative 4x minus 4. We want to write it like this just because we now want to look at it as the sum of 2 products. Right? So now we do have that common factor of x plus 1 out of those 2 products in the square bracket, so we can factor that out. We factor that common factor of x plus 1 out, and now we're left with x squared minus 4. All right, we took that x plus 1 factor out of both of these products. When we take it out of this product, we were left with the x squared. When we take it out of this product, we're left with the negative 4. Again, we want linear factors, remember, so this is a linear factor, but this is still quadratic. And hopefully, again, we notice this is the difference of 2 perfect squares, so we can factor that into the sum and difference of their square roots. All right, so like we said in the previous example, this is what we call the linear factors. Okay, now factors are different than zeros. The factors lead to the zeros. The zeros are the x values that make the factors equal to 0. Right? So the x value that makes this equal to 0 is negative 1. The x value that makes this equal to 0 is negative 2. The x value that makes this equal to 0 is positive 2. And notice each one of them only appear once, so they all have multiplicities of 1. And again, notice the multiplicities always add up to the original degree, right? So linear factors lead to the zeros, lead to the x-intercepts. X-intercepts at negative 1, 0, negative 2, 0, and 2, 0. All right. Then we want the y-intercept also. And y-intercept is generally the easiest portion of our work. And this one, again, nicely set up y-intercept, we just set x equal to 0, put 0 into the function, and we just end up with -4, right? 0, 0, 0, -4. So our y-intercept is at 0, -4. And now we have all the information we need to sketch the graph, right? We already did the end behavior, looking at the lead coefficient and the degree. We know our x-intercepts are at -2, -1, and 2. Our y-intercept is at 0, -4. And they're all multiplicities of 1, smooth curve from end to end, so we know it goes up here to this x-intercept, crosses the x-axis, and we don't know how high it goes, but we know it's all positive until it gets to this x-intercept. Multiplicity of 1, crosses again, goes down, always crosses at the y-intercept, is negative until it hits this x-intercept. Again, multiplicity of 1, crosses, which meets up nicely with our other end. So we want to label our x-intercepts, label your y-intercept, put arrows on the ends, check again, degree 3, at most 2 turns, 1 turn, 2 turns, everything makes sense. Good times. All right, I think we have one more thing to cover in this section, and that involves the intermediate value theorem. Okay, so the intermediate value theorem, again, uses the idea that all polynomials are smooth curves. That's the main logic behind the intermediate value theorem. So what the intermediate value theorem says, and this is on page 355. And this is a pretty straightforward, pretty logical idea. So all the intermediate value theorem says is if I have one x value and a second x value, then I know, we'll call this f of x, and I know that at x1 the output is positive, and I'm given that f of x is a polynomial. Okay? It's got to be a polynomial, which means it's a smooth curve. And if f of x2 is negative, then that means somewhere between x1 and x2 there has to be a 0. That's all the intermediate value theorem says. To get from here to here on a smooth curve, because it's a polynomial, somewhere, I don't know where, but somewhere it's got to cross the x-axis. Okay? You've got to be a 0 there. That's all the intermediate value theorem is saying. So the question that you'll see involving the intermediate, now we can't say, just to make this clear, let's say we have one x and a second x, and they're both positive. We can't say there isn't a 0 between those two, right? Because it might do something like that. So if they're both positive, we can't say there is not a 0, but we can't say there is. So the only absolute conclusion we can make is if one output for one x is positive and another output for a second x is negative. We can then say with certainty that there is a 0 somewhere between those two values. But if they're both positive or both negative, we can't make a conclusion. There's no conclusion to be made. So the questions you'll see is you'll be given a function in 2 inputs, and you'll be asked if you can be certain or not that there's a 0 between those 2 inputs. So let's look at an example of that. Number 34 on page 361. All right, so it says use the intermediate value theorem to show that the polynomial has a real value or doesn't. Right? So number 34, we're given this function x cubed minus 4x squared plus 2, and we want to see if there's a 0 between x equals 0 and x equals 1. All right, is there a 0 between x equals 0 and x equals 1? So, again, question, is there a 0 between x equals 0 and x equals 1? So all you do is you take the function and you evaluate it at those two values. So you put f of 0 in, very easily 0, 0, 2. All right, we know that's greater than 0. And then we look at f of 1, which is going to be 1 cubed minus 4 times 1 squared plus 2. So we get 1 minus 4 is negative 3. Negative 3 plus 2 is negative 1. So that's less than 0. So what we've just shown for this function, 0, 2 is on the graph, and 1, negative 1 is on the graph. And we know this is a polynomial function, so somewhere between 0 and 1, there has to be a 0. Yes, must be a 0. Oops. Must be a 0 between 0 and 1. Again, if they were both, if this was positive and this was positive, you say no conclusion. If this was negative and this was negative, no conclusion. Only when they differ in sign can you make that conclusion that there has to be a 0. All right, we're done for the day.